Hello, everybody. Hello, welcome to Tuesday. Woohoo! That's right. We don't get to look forward to Tuesday very often, so I feel like this is just trying to give it some respect back. So welcome to the Grit City Think and Drink. My name is Jim Gal. I'm the host and a professor at UW in Tacoma, right across the street. Makes it very convenient when I have to walk this stuff down on a cart down the street. How many people are new to the Grit City Think and Drink here? Excellent. It's nice to have people. Everybody who's been here for a long time knows the joke, but we always like to invite new people because you get to buy the beer for the first round. So we're really happy to have new people. So remember to bring your friends next time. So for those of you who haven't been here before, it happens the second Tuesday of every month. So we have a lineup through to June at this point. So we'll hope to see you back. Our next speaker, February 11th, is Sarah Chavez, who's at UW Tacoma, and she's going to talk about sort of grief and writing. So she's a writing and poetry faculty. So she does some great talks. So I hope you'll come and check that out. Our speakers here tonight, hopefully we'll learn some new cool things about how to build your own island, slowly, I guess, but relatively quickly in geologic terms. But the way this works, I'll introduce the speaker. She'll give you an amazing talk to knock your socks off. She gets to take a short break. We'll give away a few prizes. We give away swag. So I see a Grit City Think and Drink hat. So there's somebody modeling the hat right over there. So we'll give away a couple of those. Beautiful. So we'll give away a couple of those, and then we'll play Stump the Speaker with all your questions after that. Sound good? All right. And don't worry if the beeper for your food goes off. Just means you have to share whatever you bring back. So hopefully that'll do it. So without further ado, I'll introduce our speaker. Marjorie Cantine is an assistant professor of Earth and Space Sciences at UW in Seattle. Her research focuses on the ways that Earth and life change together over time and how that story is captured in the chemistry of sedimentary rocks. Marjorie enjoys long walks on the beach in both her personal and professional capacities. And I know because I actually got to go and do some field work with Marjorie, not only is she an amazing scientist in the field, she also knows how to cook for field work, which is absolutely the second most important thing to be able to do when you actually do field work with people. So without further ado, welcome, Marjorie.
Hi, everybody, and thanks for that introduction, Jim. Great. Those look like slides. Those look like my slides. Let's go. Yeah, so as Jim said, my name is Marjorie. I'm an assistant professor up in the Department of Earth and Space Sciences at UW Seattle. And the work that I'm going to tell you about today is work that I've led over the last couple of years. And it's work that has benefited from the involvement of some of my favorite collaborators and scientists at a bunch of different institutions, including the University of Washington and beyond. All of these people have contributed to these work over the years. Science is a really slow team sport, and so I just want to acknowledge all of their contributions to the work that I share with you today. I want to start out with a really big and simple observation. So we'll look at this really big map of our planet. The blue squares that you see here are selected coastal cities of more than 1 million people. And all of the countries on this map are color-coded by the proportion of their population that lives within 100 kilometers or about 60 miles of the coast. Long story short, worldwide, billions of people live near shorelines, live near the coasts. And there are a lot of reasons for that. That's true today, and it's probably been true all through human history. There are a lot of resources at the coast. Often the climate near coasts is milder, moderated by the ocean. Topography is often nice and flat near the coasts. And there's a lot of natural beauty at the coast too, which we as people who live in the Pacific Northwest can certainly appreciate. But of course, wherever there are people, we modify and change our environment. So we might do this by doing things like dredging the coast to build things like ports, building on the coasts, even damming rivers upstream, trapping sediment and preventing replenishment of beaches. So this map captures that fact that people alter shorelines. Here we're looking at this map. The coastlines are traced in a range of different colors. Hotter colors show you where the coast has been more altered. Cooler colors show you where the coast is more pristine. And the sort of summary, I think, of this map is that basically anywhere that it's warm enough that you'd like to live, humans have had a substantial impact on modifying shorelines. Understanding this modification is important, right? The fact that so many people live near the coasts means that there's a lot of people there, a lot of communities there, as well as a lot of infrastructure and investments near the coast. And living near the coast opens you up to a range of hazards and concerns that are unique to living near the shore. So thinking about things like sea level rise, storm surge, the impact of major storms coming off of the ocean. And as we modify our environment, we make changes to the way that these environments can respond to some of those hazards, affecting human prosperity and happiness as well. One particular concern is the reality that in the coming decades to centuries, sea level is predicted to rise on our planet. That is because of both just the thermal expansion of water as our planet heats up and the melting of ice caps at the poles. So here I'm showing you a satellite image to bring this home of Tacoma. This is from NOAA, the National Oceanographic and Atmospheric Administration, map of Tacoma today, and then a map of where Tacoma might be in 2100 under a predicted sea level rise scenario in their intermediate high zone. So all the areas that are highlighted in green, and I'll just flip back and forth between these again, are areas that are predicted to potentially flood by 2100. So 2100 is certainly in the future, but it's not unfathomably far in the future. We'll see if they connect the Tacoma and Seattle light rail by 2100. And so this is something that we need to be thinking about. As sea level rises, we kind of have this expectation that land is going to get flooded and we're going to lose land to the sea. But I'm going to take you someplace where that's not true today and talk about why that's not true and what we might learn from that special place to apply to other coastal areas. So to bring it together so far, we've got lots of people living at or near the coastline, making modifications to the coastline that can affect its resiliency. And we know that sea level rise is coming in the decades to centuries to come. What can we do? Well, one thing that we can do is look at places that have experienced sea level rise in the recent past, where we see land gain rather than land loss. By studying those places, we can improve our understanding of the whole set of processes that govern the balance between ocean and land, and build out our toolkit for thinking about ways to manage coastal environments and improve their resiliency. So that's what we're going to do today. To talk, so this is the part of the talk where I get to take you on a tropical vacation. So here in this satellite image, we are looking just off the coast of Florida. So Florida is here. And the island that we'll talk about today is in the Lucayan Archipelago. This is also called the Bahamian Archipelago. It's the chain of islands that includes the nations of the Bahamas and the Turks and Caicos Islands. In this image, you can also see Jamaica, Puerto Rico, Cuba, and Hispaniola. But we're really going to be focused on the islands in this island chain. All of the islands that you see here, all of the islands in this island chain are made of calcium carbonate or limestone. That is the only thing that they are made of. And that makes them really different from the landscapes we have here in the Pacific Northwest. There's nothing like a quartz sandstone or a granite or a basalt anywhere in these islands. These islands are 100% limestone, and that makes them extremely sensitive to sea level changes for reasons that I'll explain. This is a photo of one of my field sites. I'll tell you more about it in a second, but I just wanted to provide this photo to help you imagine what it is like to be on one of these islands and appreciate how different it is from the landscapes that you might inhabit. So looking at this image, you see rock, you see sand, you see water. Every single little bit of rock and sand that you see in this image is limestone. It's all one mineral. It's all limestone. It's all calcium carbonate. And every single little bit of that limestone started life as bits of matter, ions, dissolved in the ocean as calcium ions and carbonate ions, part of what makes the ocean salty. So unlike here, where you weather a granite and it turns into sand, everything that you're seeing here began its life as dissolved salt in the ocean, essentially. At some point, those ions were precipitated into a mineral. That might have happened by a clam making its shell out of ions and turning ions into calcium carbonate shell. It might have also happened without the involvement of an organism. And an analogy for that is growing rock candy from sugar syrup, for example. But in either case, it was precipitated from ions dissolved in seawater underwater. This isn't something that happens on land. Then that sediment was washed ashore, maybe blown around by the wind, and then possibly cemented together with more calcium carbonate to make the rocks that you see in this image. But what all of this means, and the origin of all of this limestone, means that this close connection to the ocean makes limestone islands very sensitive recorders of sea level, where the ocean is and where it isn't. And because of that, researchers have used the landscapes of the Bahamas and the Turks and Caicos Islands to develop very beautiful records of sea level change. All of these islands are made of calcium carbonate, so they're excellent recorders of sea level. They record beautifully detailed sea level histories over the last 500,000 years. So whenever you hear about people talking about sea level changing in North America, there's a very good chance that they're using rocks from the Bahamas to tell that story. So it's kind of a neat trick that you get to study the coming and going of ice sheets by going to the Caribbean. That's pretty cool. And so I'm going to tell you a little bit about what we know sea level has done here in the geologically speaking recent past. And to do that, we're going to look at this figure. So on the x-axis of this figure is time. 0 is today. And then the bottom of this figure, so time runs from your right to your left. So about 12,000 years ago through to today. And we're starting this here because 12,000 years ago is about when the last ice age ended. On the y-axis here, we have relative sea level. So was sea level lower or higher than today? During an ice age, you've got more of your water stored in glaciers on land. So your sea level drops. And when those glaciers melt, your sea level rises. So 0 is where today's sea level is. And then geologists and geophysicists, using a range of different records recorded in rock, think that sea level in the Caribbean looked something like this over the last 12,000 years. So you see a low sea level rising. So sea level has been rising over the last 12,000 years in the Caribbean. That initial, very early, big, rapid rise is due to the meltdown of the glaciers. And you see that that increase in sea level kind of shifts right around 7,000 years ago. That's the final demise of the Laurentide ice sheet, which is the ice sheet that covered most of Canada and the eastern US. Then, after that period of time, we have continued sea level rise pretty slowly by comparison. And there, it's actually dominated by the changing thermal properties of the Earth's crust. So as it cools, it tends to sink and subside. But to summarize this, basically in the Caribbean, we know that sea level has risen over the last 12,000 years. It rose quickly at first, and then it rose more slowly, but it's been rising the whole time. So we have a simple, relatively simple one-directional story for sea level here. And our expectation for when sea level rises is that we should see the loss of land. We should be flooding land and land should be going away. But I'm going to tell you about a field site where that's not true, where we've experienced this sea level history, and yet we have an island that has formed and grown despite this history. So that island is a little island called Little Ambergris Key, which is inside this white box. This is a Google image, Google Earth image of it. So you can see there's Little Ambergris Key, which is snuggled next to its sister island, Big Ambergris Key. One really notable thing about doing field work in this part of the world is the constant presence of the trade winds. So winds that blow from east to west, basically day and night, 365 days a year. And they carry with that, so you have winds constantly pushing in from the east. They're pushing waves. Those waves are pushing sediment. And you can see evidence of that in this satellite image in this long, kilometers long shoal that stretches off of the tip of Little Ambergris Key. This is getting even closer up to Little Ambergris Key. This is a beautiful image taken by drone by my colleague, taken actually just about 11 months before Hurricane Irma made a direct hit passing over the island. So this is really fantastic high resolution imagery of this island, just to help you understand what it looks like. So we have this sort of elevated rim of beach rock that wraps around the island, and then this interior, which is kind of like a tidal swamp. If you went and visited Little Ambergris Key, you would land on a beach that looks something like this. So you have those classic beautiful blue waters, that white sand beach. Again, every little bit of sand on this beach is a piece of calcium carbonate that was precipitated in the ocean. And if for some reason you didn't want to stay on the beach, although I don't know why you'd leave, and you walked inland, you would encounter this lithified rock rim that wraps around the island. It never gets very tall. It's maybe 4 meters, 12 feet tall at maximum. And then once you breached that barrier, you would be in the drink, back in the drink. This is what the interior tidal swamp of this island looks like. So this interior swamp is characterized by mangroves. So that's the thickety sort of bushes that you see in this image. And then also by microbes. So that thing that looks like a black shag carpet rolled out in front of you is a microbial mat composed of cyanobacteria. Walking through this, it has the texture of like soft tofu. It stinks of sulfur. It's a pretty interesting place to work. A lot of my colleagues originally began working on Little Ambergris Key because these microbial mats are thought to be excellent analogs for what life on Earth was like before the rise of animals. And there's really interesting geobiology and geochemistry happening in them. I'm going to come back and talk more about microbes later in my talk, but for right now, we're going to keep thinking about those rocks and that sand that we passed on the way in to get here. So in our initial surveys of this island, we noticed that Little Ambergris Key has some important differences from other islands we see elsewhere in the Turks and Caicos and in the Bahamas. There's no evidence of this older ancient reef core that dates to before the last ice age that we see on a lot of other islands. Instead, it seems that this island formed entirely within the last 12,000 years. At least that was our initial assessment based just on what we could observe without making measurements. Our measurements support this idea, and I'll talk you through them. But that confused us because we wondered, how do you get an island forming during a period of sea level rise? How is this possible? And so we set out to answer that question. One set of tools that I like to use when possible are historical drawings and images. And so this is the first map ever made of Little Ambergris Key. It was made by a British colonial surveyor in the 1800s. Some guy wanted to buy this island to graze his cows on it, and the colonial surveyor was tasked with figuring out what an appropriate cost would be for that. And ultimately, the colonial surveyor, I think you see that he got frustrated because he just writes swamp in the middle. He says, to make a proper survey of these keys would entail an expense far beyond their value. Which, as part of the team that ultimately did make the first proper survey of this keys, really makes me laugh. But this is the first map we have of this island, and it's kind of an interesting historical document for us to consider. The next excellent map of Little Ambergris Key that we have is this one. This is imagery shot by the Royal Air Force in the 60s. So these are really beautiful high resolution ortho images taken by flying over the island. Really lovely to look at and to compare to what we have today. This, of course, is the drone map made by my colleague. So putting all of these together and comparing them, there are, of course, issues with projection and scale that I haven't dealt with here. But broad brush, this island has had more or less a shape like the shape it has today for the last 150 years. You can even see that the position of some of these tidal creeks is unchanged. In all of these images, we have this weird little spur off of the southern tip of the island that follows a really distinct trend from all of the other features we see on the island. There's this channel here, which is really visible in the hand-drawn map, somewhat visible here, and then really visible here. So a lot of features seem to have been kind of static. Certainly, if we were hoping to better understand the growth of this island over the last 150 years, only using historical documents, it would be really hard to say much of anything. So that means we had to use the tools of geology and geochemistry, which makes me happy because that's what I like to do when I'm not looking at old historical images. And so there were many seasons of fieldwork going to this island, looking at rocks, making observations of the rocks, the environments that they formed in, and taking samples, which we then dated using radiocarbon dating. So just to broadly summarize, this is sort of how that data gets reported out in the scientific literature. These photos, I think, are more helpful for all of us. So there are basically three types of rock on this island. There's rock that pretty clearly formed at the beach. It contains shells. It contains sedimentary structures like this rollover here. This is kind of like a fossilized beach berm. You can see where you go from the flat beach to the beach dipping into the ocean. And there are even this really cool feature called keystone vugs, which only form within the swash zone of the beach. It's where gas bubbles get trapped into the loose sand as it's forming. The little grains collapse against each other, forming a keystone arch. And then, so this really is diagnostic of deposition within the intertidal zone. There are also rocks that formed after sand got blown around by wind into these large-scale dunes. So these dunes, as you can see, this is a geologist for scale, can be pretty large, like 4 meters in some cases. They contain things like fossil burrows and fossil root casts, which show us that they had to form above water, so in a subaerial environment. They contain ripple marks in them that are consistent with the trade wind direction. So again, more evidence of subaerial deposition. And then they have this classic sedimentary structure called pinstripe lamination. So very fine layering of sediment here, which is consistent with the way that wind sorts and moves around sediment. The third type of rock that we have on this island are these conglomerates. So these are sort of broken up and reworked bits of rock. The beauty of working in limestone rocks is that everything is just kind of gray and it's hard to tell apart. But if you look at some of these images, you can see that there are these big blocky chunks of rock, which look like they belong to something else. Then they got broken up, moved around, filled in with more sand, and then formed into a rock again. So we think that these formed when hurricanes battered the coast, broke up rock, redistributed it, and eventually with time relithified it. One of my favorite observations about these conglomerates is that they contain things like glass bottles. We'll talk more about these glass bottles later, but this is This is not a glass bottle that's wedged into a crack. This is a glass bottle that is incorporated into the rock. So we know that the rock had to have formed since humans made glass bottles. So this is something that has happened within the last century, let's say, the formation of this rock. So integrating those observations, we can tell from the rocks what environment they formed in. We can use the radiocarbon measurements that we get on shells and sediment that come out of these rocks to assign an age to the rocks. And that lets us understand how environment has changed through time on this island. The data that I'm about to show you are all shown in years ago, so they're ages, they're not calendar years. But the data looks something like this. The oldest ages that we measure are on exposures towards the center of the island. And then we get some old ages as well around the rim of the island. And we even get some samples that are too young to date using radiocarbon at the edge of the island. So to simplify this, this is all very consistent with the idea that there's an island that has a core and it's growing outwards. It's accreting layers on the outside, growing from the inside out. And if you look at all of these ages, these are all, geologically speaking, fairly young ages. This island has formed, these rocks have formed within the last few centuries. That's what these data are telling us. So for example, rocks recovered from an exposure in the island interior. These rocks are perhaps 300 to 400 years old, something like that. Those rocks are now 200 meters from the shore. So that is a growth rate on the order of 5 to 10 centimeters per year. So that is pretty speedy when you think about systems like this one. So this is a young island. It's growing quickly and its pace is rapid. I'll remind you that we knew this island, or we suspected that this island was probably younger than 12,000 years. But in fact, we find that a lot of this island is even younger than 1,000 years. So really pretty fast. There's one exception, and that has to do with that weird spur of rock that comes off of the southern part of the island. These rocks look really different from anything else on the island, and our geological intuitions told us that if anything on this island was going to be old, it was going to be this part. And indeed it was. But it looks like I don't get to tell that story yet because my slides aren't taking me there. I'll just highlight, so this is a direct comparison of the 1960s aerial survey to the 2016 imagery that we shot. This has been traced, so the 1961 shoreline is there on the bottom. And you can see, again, this is consistent with the idea that the island is accreting laterally, growing from the outside in pretty rapidly, so within the observational data available to us. So the old rocks that I mentioned come here from that southern spur, and they date to about 5,000 years old. So they're a lot older than anything else on the island, but they are still younger than 12,000 years. So intriguingly, this is sort of a feature that we see across the Bahamas and the Turks and Caicos Islands. We see a set of rocks that date to around this 5,000, 6,000 window of time. And then we see these younger, more recent sediments accreting around and on top of those. So this is not just a story about this one little island. This is a trend that we see within the region. And so the idea for how this island formed then during this period of sea level rise, this is the cartoon figure that brings it together, is that at the meltdown from the ice age, so this is when we're in the really steep part of that sea level rise curve, sea level is lower, all our water is in our ice caps, and the entire platform, the entire shallow water platform of the Caicos platform is exposed. You've just got water at the edge here. You've got your easterly trade winds blowing in from the east. And you have the sister island, which we know is older than Little Ambergris Key. As those glaciers melt and we start to flood the platform, we're suddenly able to begin making limestone on the platform again. We start to make sediment. that sediment and sand starts to get blown around into these large dunes. And this is the part of the island that we date that's really old. That's about that 5,000-year mark. At some point, the platform floods, the Laurentide ice sheet is no more, and we have these relict dunes, which serve as like an anchor or a spur point for the continued delivery of sediment by waves being blown by the easterlies, and accreting this island out and around until you get the modern island today. So the story of the birth of this island over the last 1,000 years is some combination of this much older, more ancient anchor point, the location of the island, probably in the lee of Big Ambergris Key, which provides it a wind block from the easterlies and a place for sediment to deposit, and the fact that there is so much sediment being produced in these waters. The chemistry is really favorable for carbonate precipitation. Another piece of the story is the fact that lithification, or the conversion of loose sand into rock, can happen really quickly here. So lithification on this island and in environments like it around the planet can occur really rapidly. And I talked to you about these glass bottles earlier. So another rabbit hole this project led me down was glass bottle archaeology. The fact that you find glass bottles in these, and these glass bottles have screw top lids, they're made of clear bubble-free glass, and they're mass produced from molds, tells you that they were made no earlier than probably the mid 20th century. So these rocks had to lithify within the last few decades or so. Another item that you can find in these conglomerates are conch, which have been hunted by humans using modern tools. So conch are these large marine snails or gastropods, which have been used for centuries as a food in the Caribbean. To harvest meat from a conch, you have to make an incision in the shell and the spire. And you can see that incision here. This is the incision that people using modern metal tools make, the sort of long, slender mark. So again, the fact that this conch is incorporated into this rock, it's just another item that bears the marks of being changed by human hands, and it's more evidence that this conglomerate, this rock, formed relatively recently. So if these bottles and these shells were incorporated into the sand, and the sand turned into a rock, and that happened fairly recently, how recently is recently? Did it take 70 years for this rock to form? Or could these rocks be forming much more quickly? Well, some observations from other researchers working in Australia in an environment that looks similar suggested to us that lithification could occur really quickly, and that it might happen in association with microbes. So these researchers did a really ingenious experiment where they took sand from the beach, they sterilized half of it, they put both aliquots of sand into aquaria in the lab, and imitated tidal cycles. And they found that within just a few weeks, rocks started to form in the unsterile sand, while no rocks formed in the sterile sand. So that, coupled with observations of close associations between microbes and new cements connecting grains together, allowed them to make the argument that the microbes that live in these rocks are an essential component of what helps them turn from loose sediment into a rock. Some key observations that we keyed into here, within these rocks from Australia, you see this thin green rind. So that's the group of microbes that we think are responsible for doing this. They're a group of organisms called endolithic cyanobacteria. And there's also this black varnish on the rock where they live. So the cyanobacteria produce this black pigment basically as a sunscreen to help protect them from the sun. And we see something really similar on Little Ambergris Key. Within the tidal zone, we see these better cemented rocks where when we break them open, we see a thin green rim of microbes living inside. really close to the tidal zone. And then above those rocks, these are much more weakly cemented. They're not as well lithified, and they don't have the same microbes living inside. So that made us, and that here's just a picture proving to you that there are this green rim of microbes living here. Are these microbes responsible for the rapid formation of beach rock and lithification on this island? So we conducted our own ingenious experiment involving dog toys. So what we did was take sediment from this island, sterilize it so there are no microbes living inside of it, put it inside a mesh bean bag. So this was made out of cheesecloth, basically, and then nestled inside a dog toy to protect it from getting rubbed against the rock. We made many replicates of these and chained them all together and then bolted them in place and left them for several months and collected them at several time points along the way. So our goal was to see who moves in, like what microbes move in, and do rocks form within these? And how quickly does that happen? Is it happening quickly enough that we can observe it? So this is what the bean bags of sediment look like after we retrieve them. You see that they've been colonized by something green microbes. And you can see that after only 5 months, we indeed began to make these small granules of rock. So this was loose sand when it went into the beanbag, but by the time it came out, we were getting little granules and clumps of incipient beach rock coming out the other side. These are some observations that were taken with a really high-powered microscope. So this is the cheesecloth. You can see the filaments of the microbes binding together these grains, holding them close together, and we think providing surfaces for the precipitation of new cements that would eventually lock the sediment together and help it form a rock here. And these observations are similar to what we see in situ, non-experimental beach rocks that we've collected from the same environments as well. So yes, we think that microbes are definitely involved in beach rock formation here, and we think that they're capable of helping a beach rock form on timescales of months, not decades. So this is exciting. This points to a set of tools we might be able to use in similar environments. Imagine if we could encourage this process to take place. It could provide us a way to lithify and protect vulnerable coastlines. And so we're beginning to explore some of these ideas at a site in the Pacific, in Tahiti. I don't know why I work in such terrible places. And so we've deployed the dog toy experiment again, but we've made some modifications to better understand ways that sediment is likely to change in the 21st century. So we now have some replicates that include microplastics. So we're curious to see if the presence of microplastics changes these lithification processes. And we're also including coral rubble. So as coral reefs die off, there's predicted to be an increase in the amount of coral rubble that's present on beaches. And we're curious to see how beach rock formation processes will change in response to these. So to wrap my talk up tonight, I want to leave you with the idea that shorelines are dynamic, they're inhabited by people, and understanding how they're likely to change in the future and building out and improving our toolkit for understanding how they will change is important to protect people, communities, and infrastructure. The island that I spoke to you about today formed really recently, geologically speaking, and it's grown pretty rapidly, geologically speaking. And that's despite a regional history of sea level rise. Microbes, even though they're tiny, play a big role, I think, in that story of how this island formed and grew. Future work is going to explore similar questions in the Pacific, so completely different ocean, and explore how other anthropogenic changes to the environment may affect beach rock formation. And just sharing this idea of people and their environments changing together now and in the past. We have evidence for indigenous occupation of Little Ambergris Key since maybe starting in the year 1000 or so. We find their artifacts entombed inside some of these rocks, which is really cool. It's fascinating for me to think about how people have lived in such a dynamic and evolving landscape in the past, how we continue to inhabit places like this, and how we can best serve both the environment and the people who live there going forward. All right, thank you.
All right, we'll give our speaker a short break while we make sure everybody has a raffle ticket, and we'll give away some prizes, and we'll come back for some questions. Thank you. All right, we're going to give away some swag. So again, as modeled by our community member out here, you can see how it looks. So remember, we are in the winter season, so this is very useful now. And as we mentioned before, if you're really hip, you wear this in the summer as well. But I'm not that hip. So we're going to give away a couple of those. So pull out your ticket. Yep, old dude. Okay. Last three numbers 734. 73. Hey. All right. Raise your hand now. You check this number. Now that man's been here for years, so just so you know, you got to keep coming back if you want to win these prizes. All right, one more. All right, last four digits 744. 744. Whoa! If you lied, this group would tar and feather you, so you're fine. So I just want to put in a plug while we wait for our speaker to come back. So February 11th, there's our next talk. Remember, the second Tuesday of each month. I'm trying to remember. Hang on. I was gonna say I'm trying to remember what the other talks are that are coming up after that, and my brain is totally fried because I was teaching all day today. So I apologize. So thank you for coming. We're gonna do some question and answer now with our speaker, and you have to just be a little bit loud because the machines in the back actually make some noise. So let's welcome our speaker back one more time.
Mhm. Yeah, great question. So I've started working with archaeologists to think about questions like this. Um, uh, so um, the people who lived here were they're called the Lucayans. They were master sailors. They used canoes to navigate across the landscapes of the Bahamas and the Turks and Caicos Islands. So one of the big limiting factors on in these islands is the presence of fresh water. And there's as far as we can tell, there's no source of fresh water on Little Ambergris Key, which makes sense. There's just not we don't think there's a water table that like a freshwater table there. But there is a freshwater table and more resources over on Big Ambergris Key. You can get to other islands by canoe. And so our model for indigenous use of these small key environments is that they were like fishing camps, probably inhabited seasonally. And that is certainly consistent with some of the archaeology we find. So this is one of the archaeological sites that we stumbled upon in the course of this work. This is an indigenous shell midden. So this is a bunch of indigenous people went fishing for conch one day and discarded the shells in a pile, just like fishermen do today. And we know that these are indigenous harvested conch because they have this round punch hole in them. So I mentioned that you have to make a punch in the spire of a conch shell to pull out the meat. People who have like screwdrivers and hammers make these cuts that are sort of crescent shape or long and slender. Indigenous people of the Lucayans didn't have access to metal tools. They didn't even have access to a lot of things like flint or obsidian that you might think of, given the geology of these islands. And so they were very clever at making tools out of shells, coral, things that they had in the environment around them. And so actually what this round punch hole is it's the spire of one conch puncturing the another conch. So they would make these punch tools out of the spire of these conchs. So this is sort of dead diagnostic for Lucayan fishing practices. So we know, yeah, again, an object modified under human hands. It's not shown well in this picture, but there's about 2 meters of rock above this conch here. This conch we dated, and it's yeah, on the order of about 1,000 years old, something like that. So yeah, it's just a lot. It's kind of cool. We don't think about archaeology as being something that's found in rocks. We think about that as being more the realm of paleontology. But here, rocks form so quickly that you do find human artifacts inside rocks. Mhm. Mhm. Yeah, that's an interesting question. So first of all, I will say that we think islands that form under really strong trade wind influence in these sort of grainy, sandy, not very muddy environments are probably existed on Earth for a long time. In fact, a lot of the early work done in this system was done by petroleum geologists who thought that this would be a really good model system to understand Jurassic oil deposits in like Saudi Arabia or places like that. In terms of like island biodiversity is a really interesting question. There are various endemic like species throughout the Turks and Caicos Islands. I don't have a great answer for you about like rates of growth or how long it would take to tip over into being like a larger sort of ecological niche. Yeah. Yeah.
So when you said that as the sea level came back up,
Mhm.
conditions that are conducive to actually precipitating.
Yeah. Yeah. Hmm. Sorry, now you guys get to see the talk sort of epileptically in reverse. Okay. Yeah, so as the sea level, so the brown in this image is subaerially exposed rock. So you're not getting any new sediment forming because that all the sediment needs to form from seawater, precipitate from seawater. But once you melt your glaciers and you begin to flood the platform, you get these little isolated pockets of water where you can start to precipitate the limestone from seawater, and then that can get blown around again. But basically, there would be net erosion rather than net production of new sediment on the platform until it's flooded and you turn carbonate production on again. Shallow sea, yeah.
Other question. Bacteria that you're using. Is it the same species? And if not, how do you go about it?
Yeah, so the so far we so yeah, it is very difficult to prove sort of experimentally what group of microbes is or isn't responsible for different things. Often the best we can do is just take a census of who's there and make sort of inductive arguments for why we think they're playing, like why we assign them the role that we think that they're doing. What I will be really curious to see is the species or the genera that we think are responsible for this process, and little ambergris key. How similar or different are those to the organisms that are doing this in Tahiti? How different are they? Um, the chemistry of calcium carbonate means that this specific mechanism is probably most likely to work in relatively shallow, warm, tropical types of seas, not necessarily the like cold or chillier rocky beaches of the Pacific Northwest. But certainly the rocks here in the Pacific Northwest also have a microbiome associated with them. And it will be yeah, I'm interested in those rocks, but still, yeah, farther out on the horizon. Yeah. Yeah. Yeah, so our there was no sterile control in our dog toy experiment. It's really hard to maintain sterility in a field experiment that you deploy over months. So we didn't even attempt it. Um uh I think the best evidence that I can give you for that the microbes are uh promoting precipitation in some way is just this field observation that the rocks in which we find the microbes are better cemented and better lithified than the rocks where those microbes don't live. And then also the observation that these cement patches are often associated with the filaments. Yeah, so here you see this fossilized filament bridge connecting two grains that's then been lithified by rock. So I wouldn't say it's like it's not a total like slam dunk one for one, but I think there's a lot of evidence pointing us in that direction. And certainly the photosynthesis that cyanobacteria like these do is enhances carbonate precipitation in other environments. Yeah.
It seems that cyanobacteria sticking things together would actually eventually, because it forms rock, which kind of take them out of the sunlight. So
Why are they doing that? Yeah. So I think there's a lot of cyanobacteria create these filaments where they trap and bind sediment. I think they're potentially just stabilizing their environment. And I think that the biofilm or the community as a whole is able to migrate pretty easily within the rock. So these filaments are not, yeah, not necessarily like occupied. The cell itself can move around within it. Yeah. Hmm. Yeah. Yes. Yeah. And you can tell me if I'm summarizing your question correctly. Is there a role for microbes in the formation of shells by like a clam or an oyster or things like that? Yeah, so far as I have a yeah, it's a good question. So something like a clam or an oyster, these animals that make their shells, or even us, we make our bones out of minerals. That all happens sort of within our cells, under control by enzymes. And as far as we know, there's not a microbial action involved in that. That's just a cellular process that we are capable of carrying out. I learned recently about something called ichthyocarbonates, which are carbonates produced in the guts of fishes. It turns out that if you're a fish living in the ocean, regulating your osmotic chemistry, so the saltiness of your blood, is a huge challenge. And one way that fish deal with that is by precipitating and excreting large amounts of calcium carbonate in their gut. And that does seem like it may be associated with organic matter and with a microbiome. So that's pretty interesting. Yeah. Yeah. So gallstone mineralogy, yeah, I think first of all, what I would say is that gallstones are like a bit of an accident. They're not something that necessarily your body is designed to produce. Um, they they're they can be produced of a lot of different things. Sometimes they're calcium carbonate. Often they are phosphates. So similar to what your bones are made of. There's also a big role for organic acids and sort of organic crud that gets caught up in them as well. There's one report of dolomite, so a calcium magnesium carbonate in the gallstone of a Dalmatian, which is a paper I think about a lot because how you precipitate dolomite under Earth surface conditions is like a persistent problem in the earth sciences. But yeah, it turns out gallstone mineralogy is like pretty varied. Somebody that I used to work with, took his dog's gallstone and made a like paper thin slice of it, and then did all this really beautiful microscopic imaging of his dog's gallstone and has it like as art in his home, which I don't take it that far. Yeah.
Remember to come back in February when Marjorie's gonna have a ball.
Yeah. Yeah. Yeah.
Thank Marjorie one more time.
Thank you.
So thank you all very much. They will come and kick us out not too long from now. So because the folks who have to clean up have to leave not too long after this. So if you wouldn't mind, if you can put your glasses in the bins back there and toss out your stuff, that would be awesome. We hope to see you in February. Thank you all for coming.